Hello, everyone. Thanks for coming to the webinar. So today is my great honor and pleasure to introduce you Dr. Liu Fang. Dr. Fang is an assistant professor at the Schulich School of Engineering, University of Calgary, and visiting academic of the Thermal Propulsion System Research Group, TPSRG, at the University of Oxford. Before his position in Calgary, he was an engineering science lecturer at an Oriel and Somerville College and senior research at TPSRG. His research interests include turbulent combustion modeling and high fidelity simulation with detailed chemistry. He received a Bachelor of Science degree from the University of British Columbia in Mechanical Engineering Thermal Fluids option in 2016, and a PhD in Engineering Science from the University of Oxford. Currently, he holds several projects as the principal investigator, PI, for the study of novel combustion chamber design and numerical study of abnormal combustion. So today he will talk about the conditional source term estimation, CSE model, hypothesis validation, and the model development. So let's see what Professor Fang can give to us.
Thank you very much, Professor Yang. Thanks for the kind introduction. Again, my name is XiaoHang Fang. You can always call me Leo. So I'm currently a new academic at the University of Calgary. I'm still serving as an assistant visiting academic at the University of Oxford. So today my topic will be conditional source term estimation combustion model, hypothesis validation, and model developments. So this is not the first OpenFOAM seminar we had for CSE model. So in this seminar, we would have less introduction on the CSE model, but more about the validation itself. Okay, so first of all, where are we? Most of you haven't heard about University of Calgary. We are a university in Canada. So we are located, we will say northwest of Canada, somewhere here, very close to Vancouver, and then probably pretty far away from Toronto, which the two cities you would know for Canada. So we are the largest city in the province Alberta here, and then the third largest city in Canada. So we are one of the biggest energy centers in the world because there are oil and gas industry here. We are very often ranked as the top 10 most livable city in the world. And then if you haven't heard of this, you probably have seen this picture from your Windows screensaver. And this is us, which is 1 hour from here, which is Banff National Park. Yeah. So a bit of University of Calgary. So we are a public research university in Canada. We are U15 member, so one of Canada's top research university based on the number of Canada research chairs. So we have a very high research budget or total revenue, which is around 1.2 billion Canadian dollars each year. And we have, as I said, very close ties to petroleum and geoscience industry with lots of opportunities in the energy sector because we are very, very close to the oil sand. So we also have recent opening for an energy transition center, just purely for the University of Calgary. And then we also have aerospace connection network. So this is about what I'm going to introduce for University of Calgary. And then now it turns to what are the main research areas I'm currently covering. So one of them is turbulent reactive flow theory and modeling. So this will be a part of the topic here, which includes chemical source term modeling, turbulent chemistry interaction, and then models relevant to conditional moment closure approaches. So we also have a bit of collaborations with the University of Oxford in terms of chemical kinetic studies, because there are combustion bombs there. We do measurements for laminar flame speed. So therefore, we would do a little bit of chemical mechanism validation and then therefore detailed chemistry software development just for the validation of laminar flames. We also have numerical studies of laminar burning velocities. So last part is relevant to internal combustion engine simulations because University of Oxford is historically led by Professor Richard Stone, So therefore, lots of the studies is about internal combustion engines. So we still do a little bit of research on ICEs, which include the novel method for post-processing, and as well as abnormal combustion for pre-chamber style design, and then relative things. But today, my main focus will be turbulent reactive flow theory and modeling. So I'm sure everyone here probably have a bit of knowledge about in terms of like turbulent reactive flows. So I'm just gonna here have a very, very brief summary of what turbulent reactive flow modeling is and what are we doing. So let's say we have a CFD solver, we would solve the transport equations of Navier-Stokes, we will solve the energy, we will solve the continuity equations, etc. So now it comes to the symbolic form of a Favre average species transport equation. We can simplify all the terms into these four things, what we call rate of change, convective terms, we have diffusion terms, and we have chemical source term. So really the focus of my research in terms of turbulent reactive flow modeling is to provide an adequate closure for the mean chemical source term, which we call omega F. So there are different ways to get these terms, which includes explicit series expansion of the mean chemical source terms. But this might not be viable, first of all, because it is very nonlinear. And then also it is very sensitive to truncation. And we might have additional term closures, which here I included some expansion for this term, which means that at higher orders, if we truncate or if we want to approximate, we need to include these terms accurately so that this can be incorporated correctly. So there are different treatments in the literature, but there are difficulties. Why is this very difficult for this then? It's because in a physical system, let's say I'm in an engine, or if I'm in an aerospace engine or a gas turbine, what we would have is something burning, right? So if it's burning, so we would have chemicals, right? So in chemicals, we would have chemistry. And then for a simple methane, we would have different scales for chemical reactions. And then this can become exponentially more complicated when the fuel becomes, let's say, higher carbon fuels or a blend of fuels. And then now we also have the physical side of things, which includes physical timescales, which is the turbulence. So we would have energy containing range, inertia subrange, and dissipation range. But if you are in a system, these do interact with each other, right? And then how do we incorporate this, which is what we call turbulent chemistry interaction? And this is one of the very essential part of turbulent combustion modeling. So what are the options? I'm not going to do an exhaust list of the things that we can do for combustion modeling, but here are some quick examples. So a lot of the studies would use well-stirred models. So what we do is that we would assume that it's infinitely fast with mixing compared to chemical reaction timescales. The advantage of this style of study is that we can incorporate detailed chemistry. We will have a direct integration approach to evaluate the mean reaction rate. Omega can be a function of the mean species or temperature, etc. But the thing is that here we only have the first order moment, or the mean of the scalars are considered as a function, and it might be very tough to include TCI without any modification of the hypothesis. And then we have another school of study here, which use So a school of combustion models, which is flamelet models. So we assume that a multi-dimensional turbulent flame can be represented by an ensemble of laminar 1D flames, which we call flamelets. So what we can do is that we think that this can be a sheet of 1D flame and it propagates like a 1D flame. And then depending on the flame you're looking at, we will be looking at a representative 1D configuration for the turbulent flame. And this could be a premixed flame on the left, and also could be a non-premixed flame. So the scalar evolution in this 1D flame can then be used to characterize this scalar evolution in a turbulent flame. okay? But here, what we have a very fundamental hypothesis is that we assume that a multi-dimensional turbulent flame can be represented by the 1D flamelet. And then this is can be true for a lot of the flame, which has been shown in the literature, but we can also pose some questions whether it is really the case. But now we have one more school, what we do as a group, which is conditional moment closure hypothesis related approach. So what we mean that is that the idea here, first, we concerning for the simulations that are not fully resolved, which includes RANs or large eddy simulation. So we have at least part of the spectrum that we are doing simulation. We're doing models for turbulence. And then therefore, what we believe is that the chemical source term is probably not a good approximation when you use a function of the mean variable and then a species, mean species or mean density. What do I mean by that? So if you're looking at the right, let's assume that this is a grid that you are solving on the right. The entire grid is, let's say, a RANS simulation. But the small grid is actually what the real resolved scale is. Because you have this well-stirred approach, or let's say flamelet tabulation approach, while you are using the information, you're using the averaged information in this entire grid to either look up or to formulate the equation. So is that a good representation? If we take an example of this flame, assuming that this flame from left to right on this point, the single square here represent the top entire square. What we record, let's say H2O mass fraction, we can see that there is a fluctuation of the H2O in these mass fractions. As you can see that maybe this is the water molecule and this is a CO2 molecule or something like that. So if we are taking each spot in it, we will see that they have different values for H2O, but is it accurate for us to actually use the average of this H2O to represent the entire grid? Our belief is that it might not be like that. So what can we improve that? One of the things what we can do is we can plot all these mass fractions for the grid and then conditioned on one of the conditioning variable or conditioning scalar. And then using that, what we can find is that it is actually a representative of a function, which means that if we're using the mixture fraction for this case for non-premixed flame, if we are plotting this point, assuming that we have all the information in the fully resolved scale, well, we can see that there might be a functional approximation for that. And then therefore, what we have to do is that we will see that we will have this approximation here, which is the first moment approximation. And this is the foundation of conditional moment approach. And then similarly, it is a foundation for CSE as well, conditional source node estimation. So there's one very important assumption we had here is that the conditional average does not fluctuate too much in space. So let's say if we take small squares here and a small square here, if we are considering as the same CSE solving procedure, this fluctuation cannot be too big. So that's a very important assumption we make here, okay, which we will come back later. So how do we actually solve the conditional average then? So here, how do we actually solve these terms and to actually gather these terms? So there are different ways. I'm sure you have heard from Professor Matt Cleary's talk, as well as Professor Salehi's from Sharif, talking about their approaches. And then here we also include conditional moment closure, which is originally from Cambridge, I believe. So what we can do is that we can do the transport equation as well. But as you can see that if we do the transport equation for conditional variables, that what we would have is a lot of additional terms, which might require additional modeling. And this has turned out to be very difficult as well from the literature. And then the extension of this might be difficult as well. So what are we doing then as CSC? How do we mitigate it? This difficulty in terms of gathering the conditional source term, but while keeping this assumption correct. So if we believe that, let's say, conditioning variable is a better representative for getting the chemical source term, what we would hear is that in a CFD module, let's say if you are an OpenFOAM solver, what you can get is the unconditional variables. Let's say if I'm solving this time step from the initial states, I know that for here, what I can give is the unconditional variable, let's say here, a water mass fraction. And then what we would have is, let's say if the conditioning variable is a mixture fraction. And then let's say if we know the probability density function of the mixture fraction, and then what we ended up is this function, which is the integration with probability density function with the conditional average. And then we add it together and we can get the unconditional variable. And then this B here is given by the CFD module. And if we know X, which we actually can do, because for a lot of the flames, let's say if we're using the conditioning variable as the mixture fraction, we can have a presumed PDF for that, which is better represented by beta function. And then what happens to this is that this can be overly simplified, to a function that is AX equal to B. So what we are really interested is the X, right? So A is a probability density function, B is given by the CFD. So what we can do is really, we just need to have inversion, right? So we can have X equal to B times A negative 1. So we can get the inversion to get the X. This is exactly what we want for this function, right? So now this is a simplified routine, and then the implementation I think was covered before. So I'm not gonna repeat it again, but it's more about the theory for this talk. So now we would have mixture fraction variance from the CFD, and then we have a presumed PDF. We assume that is a beta if the conditioning variable is mixture fraction. And now we have the unconditional mass fraction, and then we use the CSE routine, which is inversion processor. So there are a couple more mathematical regularization we need to use, which I will introduce later. And then we can get YK on the condition of mixture fraction here. And then we use a chemistry lookup here. And then therefore we can include turbulent chemistry interaction here because we included the mixture fraction and its variance. And therefore we can use this routine. So how do we actually implement then? So first of the things, what we want to do is we want to pre-allocate CSE ensembles prior to runtime. So for a flame shown here, what we can do is we can dissect the flame into different ensembles, which horizontally. So for each of the ensemble, we consider it as a CSE routine package or routine space. So then we would have overlapping ensembles just for the sake of smoothing or for the sake of like a continuous solution. And then each ensemble can be assigned to a processor, ideal for flames with clear symmetry. That is very important. And then this has been successfully implementation in Sandia methane co-flows, CDEF. So what do I mean by matrix inversion here then? So for each of the ensemble, let's say for each of the square you see on the previous slide, what are we actually doing for CSE? So for CSE, what we do is we will have the probability density function. What we want to know is really the conditional variable here. And then what we would have is the unconditional from the from the CFD solver. So here there is a condition. This has been done by a lot of studies. So what we found is that the number of CSE points in an ensemble has to be a minimum of 10,000 points. And then N is the number of PDF divisions, usually is 50, which means that we would have 50 values for a mixture fraction as a bin. So here there are different ways of regularizing because because it's an inversion, and then it could be EO-post, because of the size of the matrix. So therefore, we have to do a little bit of the regularization, and then there are various ways of doing this. So what we have chosen is Tikhonov regularization, just to get a stable solution for inversion. And then because it's a huge matrix, imagine in your computational domain. So therefore, we will do a little bit of reduced matrix through linear algebra. So therefore, we can reduce the size of the matrix when solving in each ensemble for each processor. And then there are, we use LU decomposition here. And then later on, there were some additional implementations by different groups to improve this inversion. And then for chemistry, so what can we do for chemistry? Here, what we use is a traditionally used TJODM chemistry lookup table, which is used by PDF methods. So TJODM lookup here is constructed for a methane flame, which is based on mass fraction of CO2 and mass fraction of H2O. So what we have here is that we can, using TJODM, it separates the timescales in chemical reaction systems. And then the TJODM manifold reduction is based on IODM by using trajectories. So for the trajectory, it is simply the path the system takes through the composition space from the initial point to the chemical equilibrium composition. And then here, what we choose mass fractions of H2O and CO2 as a progress variable. And this has been studied for quite a lot of studies, and then for methane flames. So now we can do a direct comparison between CMC and then CSE, and this has been published as well. So what we would do is for CFD module from the top left, we would have very similar things compared to these routines. The top routine is the CMC, the lower routine is the CSE. So the only difference what we would have here is we might have a species solved right away. So therefore, we can have direct access to PDF and inversion. But in the CMC routine, what you would have to do is you have to solve n-1 transport equations. If you are considering detailed chemistry, that will be extremely expensive. And also, for CSE, then what we can do is we can use TJODM that can consider detailed chemistry, which is significantly cheaper compared to CMC in terms of that part of the implementation. However, there are also some CSE drawbacks here, particularly what we would need to do is for the MASH, for the conditional average, has to be very high. What does that mean? That means we need to have a minimum amount of cells in the ensemble I just showed. So then the question is, why is that? But I will do that later with a detailed explanation. But for here, for the comparison, what we can see that at least for a lot of the flames we are considered and we're considering these days, CSE does as good, at least as good as CMC model, and possibly with a lot faster computation. So here are some selected CSE work in the past years, initiated by Kendall Bush, and then obviously added by a lot of other researchers. So what we have here is that we have done non-premixed flames, premixed flames, and as well as recently some partially premixed flames, which I will cover later on. But here, what you can see is that the majority of the fuel that considered here is methane, because it would have a very stable TJODM manifold. So what we have here, only one is N-heptane, but this is an a priori study for a high pressure flow, which has been proving that CSE can do this, but this is not an a priori, sorry, this is not a posteriori study. So most of the fuel have done is limited to methane or simple fuels. So then during one of the discussion we had is that what if we actually incorporate something that is very good from flame generating manifold, which is constructing manifold for different fields, and then we can use detailed chemistry to generate that. And then incorporate the CAC ideas into flamelet. And then here, what we use is that we only use the flamelet generating manifold as a chemistry lookup. So whereas the turbulent chemistry interaction can be solved by the CAC model. So what we have here is similarly, the only thing replaced by the previous implementation is that we replace the TGODM with flamelet generating manifold. And then everything else with a little bit construction, because we're using flamelet generating manifold. Now, for a non-premixed flame, we use the Z as a mixture fraction, and we use a conditioned progress variable to look up for the flamelet generating manifold. That's the slightly change from the flamelet generating manifold. But what we believe that CSD can be a bridge between these two methods, because we can use CSD as a fine tool, because through the very beginning of the model, we didn't make an assumption for what region the flame has to be in. So whereas for a flamelet model, using as a combustion model, what we would have is at the very beginning, we would be assuming that flame located in a flamelet regime. So that's a very big difference between this implementation and then the other implementations you would see from the FGM type of model. So, but the constructing of the FGM will be very similar. So we will be starting from a mixing solution, which is an igniting counter-diffusion flow, counter-diffusion flamelet. Because this is for a spray case, so spray A, therefore we have to include the igniting behavior of the spray. And then it is simulated until the quasi-steady state to capture the ignition process. And then therefore a series of CDFs at decreasing strain rate are then simulated to capture the regions that was not covered by ICDF. And then therefore a typical coordinate transformation from physical coordinates X and T will be transferred to progress variable and then mixture fraction space. And then the 2D manifold can be generated. The good part here, you probably noticed that is that we only constructed 2D FGM, which we can still include the turbulent chemistry interaction into it. There are more advanced FGM approach, which can include this, which means that your manifold can be in 4 dimensions or even 5 dimensions, but that also can significantly increase the lookup time, which there might be some mitigations. For example, there are some studies lately using neural networks. But for this approach, we didn't need to increase the size of the flamelet generating manifold to include turbulent chemistry interaction. So as a validation case, what we have, we will use the endodecane case because it's well validated and well studied. And then obviously this is a spray A, which include the non-reacting and reacting endodecane, because at the time the project was mainly focusing on diesel engine studies. So what we have is reacting cases with increasing oxygen concentration as well as different gas compositions. So what we have found is that, first of all, we implemented this in LES, but this can be directly transferred to RANS as well, because this approach does not have limitations in terms of implementation with RANS and LES. So this was found that it's capable of doing capture 2 stages of combustion, which is the characteristics of this spray A. And then we also compare with the Schulich image on the instantaneous temperature field from CSC FGM, which is on the right side, and the simulation on the lower part compared to experiments. And then perhaps more encouragingly is what we found is that we can actually use this CSC FGM type of model to actually capture the scalar dissipation rate and its evolution with the flame extinction and then reignition. Although we believe that there might be more improvement for this model at the time because we use mixture fraction only to capture ignition, but we can still find it, which is a very encouraging point for us to continue working and improvement of this study. And then here are some results has been published before for CSE FGM type of approach. So what's next then? So when we come to the question is like, okay, what do we have next? So we have premixed combustion using CSE, which was covered by Professor Mahdi Salehi, and then non-premixed, which I've just shown. And then now we have a more realistic representation of the flame, which would be partially premixed. So this is undoubtedly the more realistic compared to the previous perfectly assumption for the flame configuration. So what can we do? What can we do to make this happen for partially premixed flame? So one of the things is that maybe CSE with more conditioning variables. So instead of using, let's say, for premixed flames, what we use is progress variable. For non-premixed flames, we use mixture fraction only. Maybe we could use mixture fraction and progress variable together to make this happen. But what are the challenges of that then? So first of all, we want to say that, is it vital to neglect spatial gradients for partially premixed flames? So first of all, if you remember that for each ensemble, what we assume that the conditional fluctuation is not very big in that domain, which means that the conditional fluctuation will be following a function, and then it's not fluctuating that much. And then for a partially premixed flame, is that true though? The second question we had, and then if that's true, then how many conditional variables do we need for partially premixed flames to make this variation very small? So this is the question one we want to see. So typically what we have for mixture fraction, we will have Bilger's definition. And the second question is concerning the progress variable as well for premixed flames. Because for progress variables, for a lot of the different studies, even within the FGM community, there are a lot of definitions of progress variable, because at the end of the day, these are all artificial variables we defined. So some studies have using, let's say, CO2, some has been using combination of CO2, H2O, some of them even include formaldehyde and different things. So is that going to affect the conditioning variables for our flame? We don't know. We can't say that CO2 will be the best for partially premixed flames. And then the question three is that we can get the unconditional species mass fraction, for example, from the CFD routine. Now, if we have two conditions or even three conditions, so what we have is a mass fraction with the probability density function with these two things. But what is the probability density function of this joint probability density function? So a lot of the things studies assume that presumed PDF approach with statistical independence. But however, it's intuitive to think that it's probably not true, because like how can mixture fraction and then progress variable inherently uncorrelated? So, but we have to check that. And how does this assumption affect what we are doing here? So now, so most of my research from this point is really not OpenFOAM implemented because it's theory. So what's the best way to approach the theory is that we can forget about simulations. So what we do from here is that how about we just use the experimental data to prove that our study is correct? Can we do that? Therefore, we don't have to argue that we have to find the best DNS to choose it. And then we don't have to really find a way to compare or validate it with the case which set it up by us and then the experimental list together. How about we just directly use experimental data to actually do this? So here what we use is the Sandia TUD flame series, which is available publicly. So, and then what we think is that what we can do is question one, is it valid to neglect spatial gradients for partially premixed flames? So if you remember the flames, what we have just done for a CSE implementation, for this flame, what we have done is that we use different blocks radially, right? So we 1 block, 2 block, 3 block, 4 block, 5 block continuously. So what we have did assumption is that at least for the radial direction, we assume that there is no spatial fluctuation because we're actually grouping them together. But our assumption next one is that on the axial, there might be difference. That's why we separate it together. So following this direct assumption for our model construction, what we did is that we just grouping all the data from the experiments and then see whether this make a difference. So what we have done here is, first of all, we did use Sandia D. The difference between, if you're not familiar with these flames, flame C, D, E, F would have different Reynolds number and with local extinctions from none to little to moderate and to intense. So what we want to do here is, first of all, what we have published in terms of a study, which is the flame D. And so we take out the flame D separately just to study whether these assumptions are correct. So what we had done here is that we have 2 directions, which is a radial direction, which is the axial direction. So these are the mass fractions of the conditional fluctuations of the species mass fractions directly from the experiments. So we take out all the experimental data radially and axially, and then compared with the conditional average of it for each location radially and axially. So what we can see from the radial direction, from this direction, you can see that for each of the radial direction, it doesn't make a huge difference. So if you look at horizontally, so the only difference really showed up, which has a drop, which means that it's probably not a good approximation for no conditional fluctuation, is somewhere around the nozzle. But it's very understandable because this is a flame, it's a Sandia pilot flame, which means that you might be expecting some unsteadiness or like at the very exit. But because of the easy implementation of this model with one single conditioning variable, we will be able to produce very, very good results as comparable as CMC. So therefore, we think this assumption stands here. And now it comes to the axial conditional fluctuations. So first of all, a bit of notation. So what we have is that we have conditional fluctuations of the species around the circle, which is the average of the conditional fluctuation. And then we also have all the points at the axial location, and then marked right away using gray dot. And then these are shown a local average of these normalized around the normalized conditioning conditional fluctuations. And the plus minus sign is RMS. So from here, what we can see is that there is a difference in axial direction, although the conditional fluctuation average is around 0 anyway. Okay, but we can see that there are quite a lot of fluctuations here. And then we can say that the fluctuation changes differently between axial direction. And this is actually a very valid proof for our method, is because we didn't assume that each axial location is the same, because we actually take different axial location as a different ensemble to do our CSC routine. Okay, now it becomes a bit more interesting, because when we have extinction, so what we have done is that instead of with extinction, what we believe is that we should really have doubly conditioning. So because we're using doubly conditioning, if you imagine that if we have 50 bins for mixture fraction, which means you have to have 50 numbers into the mixture fraction, and then now we have a progress variable, the minimum progress variable we had is 30. So that means that in order to analyze the flame, we would have at least a bin of 1500 each point. And that is a lot of experiments. And then we thought about, okay, what happens if we combine all the flames? Because what if our hypothesis is that when we combine the entire flames, it doesn't really matter. Like in the radial axis, even if it's a different Reynolds number, you would have conditional fluctuation that does not change that much in the radial axis. That is in fact correct. So if you remember from here, this is the single condition for flame D, which has a drop at the very front of the flame. But now if we actually change to doubly conditioning, as you can see that the conditional average is not changing at all in any radial axis. And now it comes to the actual axial axis. We can see that this seems to be a bit bigger, but at least it's uniform. But if you look at the scale of this, it's 0.01. But if we come back to a single fluctuation, it's actually way bigger. It's 0.05 for mass fraction. So even if we combine the flame from C to F, use the doubly conditioning hypothesis, we're expecting no or almost to zero conditioning fluctuations from the radial axis, and then reduced axial axis conditioning fluctuation. This makes it a very good argument for doubly conditioning CSE to work for these type of flames. And these are the average fluctuations as I have shown before. And here what we have seen is, again, there are small scattering at the very beginning of the nozzle, but everything else is, at least you cannot say there is a functional decrease at a lot of the points for these types of flames. And again, a lot of the flames, especially data at flame F, is with extinction. So therefore, there might be some scattered points, but bear in mind, this is included without any additional pre-processing at the very beginning. Okay, so all the results here is the hypothesis test directly on experimental data. So now we have included the diffusion flame that we have studied with extinction, and then we want to include a bit more. But before that, a bit of conclusion from this study is that we can see that single conditional averages were seen to vary downstream directions. It was shown that the conditional fluctuations radial direction did not exhibit any clear functional dependence, especially after the nozzle, which is made to validate the assumption that there's no spatial dependence of the single conditional average in the radial direction. And then using a single global conditioning average for flame D, which is a mixture fraction, might still give acceptable predictions of the reactive scalars in CSE calculation. For flames C and F, the analysis were performed by ignoring not only all spatial variations, but also by lumping the four flames together to generate a global two conditional average. So it was found that the conditional fluctuations do not exhibit any significant dependence on either spatial location or even on Reynolds number. So furthermore, the normalized RMS of the conditioning fluctuations were found to be dramatically lower for the two conditioning test as was found in the one conditional test. This gave you a very, very good foundation of, let's say, if we want to have a flame that includes extinction, reignition, or possibly partially premixed flames, we might want two conditions. And in fact, there's an additional study I was not showing here, which was included to study the bluff body flames from Sydney using the similar terminology. It was found that if we include a third conditions, we can actually use it as a one single space to use the three conditional average to solve it. And then in here, a very interesting question proposed was that what if we have a method, have conditioning variables, which represent the point on the flame that use, let's say, mixture fraction to actually capture the mixing. We use progress variable to capture what is a reaction progress. And last one is enthalpy. If we include these three things, which would include almost every phenomenon in a flame that needs to be included. But that's one thought, and then there are additional studies need to be done. But furthering previous studies, what we have done is that, okay, we did extinction with non-premix. What about partially premixed? Okay, luckily we have some colleagues at Cambridge that did swirl burner as well. So we have premixed, moderate, partially premixed, and highly stratified, which are good representative of partially premixed. And now with this data, what we can do is that we can use to study our question 2. Obviously, still come back to question 1 as well. Is 2 conditioning good? And then second one is what conditional variable for partially premixed flames? Is it important for CSE at all or no? So what we have here is for swirl burner, we have premixed flames, but because of the stratification we have, it can be considered as partially premixed at some point, okay? So now we have flame exhibits various stratification and swirl intensity. But here, same as the Sandia flames, but now we can use principal component analysis because one of the things we want to study is conditional variables, what conditional variables. So there are many techniques instead of we choosing it directly because we have the data, right? So we have the data, which is methane flame from Cambridge Sandia swirl burner. And then we have 5 million point-based measurements of temperature and major species. Because we have major species and temperature, and then it's a 5 million points, you can literally treat this as a single point measurements or large eddy simulation of experiments. So what we can do is that we can use principal component analysis to parameterize a given data using a reduced number of variables to see which variable is most significant in representing this flame. And then therefore, what we can do is that we can study whether the extracted progressive variable is a good option for doing this simplification. So what we did is indeed we choose different scaling methods based on suggestions from colleagues. And then we have defined 4 different progress variables that is based on the PCA analysis, which I'm not including here. You can find details in the paper. So what we have done is that we use progress variable 1, a little bit surprise to us is actually temperature is a good progress variable to representing this. Maybe not too much surprise because it's stratified, but one of them is temperature. Now, next one is CO2, which we usually use anyway, and then CO2, CO, and CO combination of H2, H2O, and CO. So this is directly data extracted from PCA, and also we correlated to things that we found in the literature is a good representative of progress variable for this as well. So now what we did is that we did progress variable combination for the study of this. First of all, there's one combination for progress variable, a single condition. Because it's a premix flame, so a lot of the studies will use progress variable as one conditioning. And as you can see, the RMS of the conditioning fluctuation for different locations with different studies, we can see that first of all, singly conditioning variable does significantly more has doubly conditioning flames. Not that they're not good, but still, if you compare with the doubly conditioning CSE, it's and then therefore what we and then here, just to mention again, this is including all the flames in the swirl burner all together doing the analysis, where we didn't repeat the study on the spatial fluctuations on the radial axis because it was proven before. Therefore, we didn't do it again. But here, what we did is that we found that very interestingly for this type of model, the definition of progress variable here doesn't make a huge difference, at least from what we have studied here for mass fraction of these species, which is included by the measurements. That gives you a very good opportunity for the combination of this method with FGM, because FGM sometimes might struggle with the definition of progress variable, and then you might need different approaches. But if we combine this hypothesis study that we found, and then with the FGM, the advantage of FGM using different species to construct manifold, maybe we can have a better balance between these two models as well. So therefore, what we had done is that we proposed one of the things what we want to do is MR FGM, multi-regime flame generator manifold. This is not a doubly conditioning idea. This is still a single conditioning, which we have two different FGM, one with diffusion FGM, one is premix FGM. Therefore, we can look up and we use a criteria to dissect what's actually premix, what's actually non-premix. And this is following very closely to MRFGM. But in this case, we can include, again, turbulent chemistry interaction through presumed PDF. And then there are another approach what we have is doubly conditioning source time estimation. I'm not going to cover it, but this actually will be covered by Professor Cecile DeVolt in an upcoming series because she is dedicated to her study to doubly conditioning source time estimation. Whereas what we do here is with FGM combination as well as the hypothesis test. So this is one of the ways they have done, and this has been shown that it gives very accurate results for a mild combustion, as well as partially premixed flames. Obviously, this is supported by the hypothesis study we had. And then this is what we have today, very short, brief studies on why do we need CSE, why this is a good idea. And obviously, because we have more studies to come and more hypotheses to come, as I've shown here. So we only cover question 1 and question 2, but a very big chunk of the study is that what the best probability density function is needed. At the moment, usually what we have is beta-beta function connected for progress variable and mixture fraction. But do we need more? Try something else. And what an a priori study would show. And then because we have the Cambridge slope burner, can we just directly reconstruct it from the partially premixed flame measurements and then see what is the best joint probability density function from there? So we still have question 3 to be covered before we do a lot more implementation. But that's everything I had for today. So I want to acknowledge my collaborators and then the people that have actively worked on this project, Dr. Riaz Ismail from Oxford, Dr. Nicholas Sokolarek, which is used to be a student with us at Oxford and now is on Surfax. And then we have Professor Kendall Bush, who is the pioneer for this model. And he's also my undergrad supervisor, and Professor Mahdi Salihi, who's a good friend also from UBC. And then the implementation is mostly from Mahdi as well. If you're ever interested in this type of model, you can approach us and then we will provide you the correct thing if you're interested. And obviously we want to thank Professor Alessandro Parente for the help on the PCA analysis, Simone Hodgegroup for the Sandia data sharing, as well as Musemi. So last but not least, I have 2 minutes left. We are hiring. So I still have one fully funded master project on joint probability density construction at the University of Calgary. So the application is 31st. So feel free to contact me if you're interested. And I'm also hiring together with Professor Felix Leach with a new project code that is coming soon. It will be posted within a week, hopefully. It will be a 1-year PDRA, postdoctoral research assistant, which will be working affiliated to University of Oxford for the study of DCESE construction and hypothesis. So the application will most likely by February 7th. So feel free to contact me. Bear in mind the 2 applications should go to 2 different emails. So thank you very much for your time.
Thanks, Professor Fang, for a very solid and excellent work. So now is the time for Q&A. So far, I haven't seen anything in the chat, but so for the audience, please feel free to speak up, especially those on the panelists. I think you can just unmute and ask a question to Professor Fang.
Hello, Dr. Fang. I'm Wei Yao from Institute of Mechanics, CS. Thanks for your presentation. It's very interesting. And I have 2 questions. First, it seems that you didn't solve the inversion matrix for the whole domain, but instead you regroup the CSE elements into different groups and then assign them to different CPU processors. So my first question is, which criteria are you using to regroup the CSE elements, and why did you do that? And
yeah. Okay. Do you want me to go through this question first, and then?
Okay.
Yeah, I have very bad memory. Just apologize first. So first thing is, what are the criteria to grouping this? So what we have is just physical dimension. The reason why this is actually the very main purpose of grouping this way is because we did the a priori studies later on, and we verified it's actually okay. So this is why we want to study all these theoretical studies, just to see, okay, is this matter for radially? How much matters more, or how much matters less? So from our case, at least from what the experimental has, which is 20 per ensemble, because for the experiments, you can just assume that it's 20 per ensemble. But just in case, what we have, the criteria is that as long as we have, let's say, 0.95, 0.1 here, 0.01 here meters for axial axis, we assume that it is ensemble. Yeah, so it's just physical division. Yeah.
Okay, I understand. Okay, my second question is, for CSE estimation, sometimes you will get unphysical values. For example, the negative temperature and the mass fraction larger than unity. So, have you done any correction on the CSE estimated values? So, how did you treat this?
Yes, so one of the things you have to remember that there is a major flaw on this for this method, because we use mathematics. It's actually not a conserved method. So that is a very big flaw, which we admit. But because the advantage takes way ahead of a flaw. So what are a good way of regularizing it? It's really depends on your technique of regularization, because my approach is based on FGM. So one of the good ways to regularize it is with FGM solution, because when I was doing it, what I regularized with FGM, but there are different ways of regularizing this. So one of the ways, again, it could be previous time step. So if you're regularizing against the previous time step, you usually would have a way better continuous solution. So that's why we have technique of regularization, where here you can input either FGM model as a regularization parameter, or you can use previous time step. So that's my answer to your question. Yeah.
Okay, thanks. I have no further questions. Thanks.
Yeah, no worries. Nice to meet you.
Thanks, Professor Yao. So any other questions?
Hello, Leo. Can I ask you some questions?
Yes, of course.
Yeah. You mentioned that you initially you introduced CSE model with a single conditioning variable, right?
Mm-hmm.
And then you move to the double. So how about the computational cost when you move from single variable to second one?
You would increase. First of all, what you would think is that you would, on the transport equation itself, you would have at least 2 more transport equations. Okay. For progress variable and double prime of progress variable, which is variance of progress variable. Mm-hmm. And then you would also increase the size of your tabulation, because now you have a slightly bigger table, which include different parameters. Okay. Right. And then you also would have a joint probability density function, which is slightly more complicated as well. Mm-hmm. But I think it is worth it, because we are very confident. This is one of the models, we can produce very good results for partially premixed. So the compensation for this is good. And also you don't have, remember, this is a model that can cover studies that are unresolved. So you don't have to go to very fine grid to actually do this, because you would base on the physics thinking that progress variable is based on either beta function, hopefully, or clip Gaussian, or mixed refraction is based on the PDF of beta function, which is proven by experiments as well as DNS. So therefore, the computational cost might even get lower because of the actual computation is involved anyway.
Okay, yeah. Okay, because I remember actually the people from University of Cambridge, they also developed, a double conditioning CMC. Actually, the computational cost probably will increase very quickly. So I'm not sure if you compare the double conditioning in CSE and the double conditioning in CMC, these two methods, because here, I guess all the comments here are based on single conditioning variable, right?
Yes.
Yeah.
Yeah, we haven't compared because we haven't got a case that they did similar to us. So, so that it wouldn't be fair to compare two methods with two different cases.
Yes.
If if that makes sense. But if opportunity comes like this, say CMC did Sandia D and CSE did Sandia D as well, and then for them they did SWO, we did SWO, and then I think that will be a perfect fine study. Yes.
Okay. Yes. Thanks. Another question is I think you also consider spray frame, right? So for spray frame, I'm not sure if your flamelets, your conditioning flame structure considers the evaporation turn effect or not. So
no, it's the particular for this flame. We assume that because it's a diesel flame, so the flame is actually not anchored at anywhere that is interact. Well, we assume that it's not interact with the spray, so it's actually a gaseous fuse somewhere here already.
Okay,
so
that means that
yeah.
Okay, so that means that your model is still from gaseous combustion, right? Gaseous phase combustion, right?
Yes, mine is, but Cecile, which hopefully she will talk very soon, is not. Okay. Yeah, so it can be incorporated to spray already. Yeah.
Oh, okay. Yeah. Okay.
Yes.
Yeah. Thank you very much. Thanks again for your introduction for the CSE model.
Yeah. No worries. My pleasure.
Yeah. Okay.
Hi, Leo. Hi, Professor Yang.
Oh, hi.
Hi.
Hi. Yeah.
May I ask you questions? Yeah.
Yeah, of course. Yeah.
Okay. So for the previous question about the spray combustion, actually we have done some work on the flamelet modeling with we consider the evaporation in flamelet modeling. So maybe yeah, we can discuss this later. My question is, you have incorporated CSE and the FGM model in your simulation. So how about the efficiency of the simulation?
Obviously, there's no argument that FGM will be faster than us. But I think from a theoretical point of view, just from my personal view, for a simple implementation of FGM like this, which a lot of people would use, there are advanced ones. What I would believe that this model give you better representative physics. So you would be more expensive in terms of computational cost. But as I said, you can even use this for RANS simulation. It will be fine as well. Yeah.
Mm-hmm. Yeah. My second question is, I think in these days, many people they are working on incorporating ANN and to flamelet or FGM. So, do you have any comments on this approach?
I welcome anyone that has a manifold that is very easy to use. Obviously, I think in manifold reduction or manifold representation, it kind of makes sense using ANN because we would have a better representative of the lookup because ANN does a very good job in interpolation. But in terms of the actual simulation, I'm not sure. I haven't tried, but I'm happy to learn. Yeah.
Okay. Okay. Thank you. Thank you. That's my questions.
Yeah, no worries.
Hi, Leo. So maybe I can ask some questions.
Oh, okay.
So yeah. So basically, I think you try to say the CSE is more applicable, broadly applicable than, let's say, the flamelet or flamelet type approach. But
no, I don't want to say that. I don't want to
yeah,
say that. Just to clarify, there are advanced techniques to improve flamelet. Let's say the multi-regime flamelet, as well as flamelet includes various other dimensions, which you can have flamelet has double prime of C, double prime of Z, and then even scalar dissipation rate. But for if you're comparing a simple application for this type of just two-dimensional FGM, I think CSE a great addition to it. Yeah, so that's my argument.
So I basically try to figure out when you introduce CSE, in my view, all the assumption hypothesis looks the same as the different flame. I mean, you can start with the basic flamelet and then say FPV or other things. Is there any assumption or hypothesis actually different? And because that will indicate the difference in applicability, right? Because I mean, in the flamelet world, people didn't say in the same language as how you describe CSE, but it's actually like that. It's also the conditional, right?
Yeah, but so the CSE assumption is really from CMC. I think
yeah, even CMC is, I mean, it's a kind of a similar idea of flamelet, but yeah.
Yeah, it could be, but I think there's a very big argument in between as well. So I don't want to get involved into that.
Sure. Yeah.
But I think, yeah, at least from my understanding is that flamelet, you would assume that the flame is located in the flamelet regime. But
that's
from
the 1980s flamelet.
But still,
yeah.
But I don't want to get into this argument, to be honest.
Because I believe in your development, especially you mentioned you want to add more variable, later add even enthalpy. I believe that's directly learned from what already happened in the flamelet side, because they are doing the same way, adding more variables. And right.
Yeah, so we actually have a theory paper that was deriving equations from the conditional moment hypothesis to actually achieving the multi-region flamelet equation as well. Yeah, so you can directly driving this approach and ended up use if you are including three conditions. But my take on this is that I think there are very little studies using three conditions from the multi-region flamelet combustion model.
RFPV have the Z, C, and H, exactly like what you mentioned. Yeah.
I think the implementation for that is also extremely expensive, if I'm not correct.
Not really. It's the major issue is the table dimension is high, then your memory become an issue. And the shared memory is the challenge you need to tackle. But that's already solved like 15, 20 years ago. Yeah.
Okay, that's good.
Yeah, but I think your validation of those hypotheses here actually also applicable to flamelet community, because they actually need the same hypothesis or assumption, but I don't know whether anyone validated to the extent you did. So I think that part of the work is not just useful for CSE, but it have a much broader impact.
Thanks for your comment.
Yeah,
I'm happy to discuss.
Right. Yeah. My last question is, I know you haven't reached there yet, but what's your opinion about or idea about the joint PDF? What's the right direction to go?
I actually talked to one of the panelists from Penn University. So I think one of the methods he had was very good. Copular, I think Copular is a very good opportunity for this, because we did actually a priori, not me, but personally, but Kendall did a priori study on DNS just to test how much error that is included in this entire model. It turns out that the joint probability density function is the most. That's why we want to tackle this. And then because we always use beta-beta or beta-clip Gaussian, so we think there are things that people has done, which I remember Professor Chen Zhi has done something about it. So that's why we approached to him as well. I think copular is a good way, and ANN might be, but in my view, maybe I will try copular first. Yeah.
Okay, thanks. Now there's a question in Q&A, looks like.
Yeah, okay.
Yeah, so this is Shirinva Saron, and he said, why implementing CSE model in OpenFOAM? Any actual libraries need to create apart from the inbuilt library in OpenFOAM? Whether do you need any actual libraries?
The entire model is the actual library. And this is quite a lot of PhD's work. So my part is adding a little bit on top of it. But we have Professor Schulich, which done 15 years ago. We have Kendall has done research on 20 years, and I've only did 6 or 7 years on it. So there are a huge library which we call CSA form. Yes. So every single steps that we showed, it's actually a bit more complicated than we just shown here. So every single step is really a package library. Yes.
Okay. Yeah, so I think this is a good answer, but if the audience have a further question, you can put. Okay.
Yeah.
Yeah.
Okay.
Yeah. By the way, actually, I have a question follow up what Professor Wei Yao asked. So you did that partition in space, right? And you have a very good evidence you justify it. But let's say for a practical engine combustion, which you don't have such a nice orientation of a jet flame, how would you do the partition in an arbitrary complex?
That's why we did bluff body validation as well. I didn't include here because it's a bit more complicated to show it. Yeah. So what we can do is there's 3 conditioning with enthalpy. That's a hypothesis we said. It's like if we have enthalpy included, if we have mixing included, if we have reaction progress included, we don't need partition.
Okay, then it's insensitive on how you do that. Yeah. Okay. That's good.
There are engine studies of CAC before, I think. Yeah.
Yeah. Sure. Yeah.
Thank you.
Any other questions from any audience or panelists?
Happy New Year, everyone.
Happy New Year, everyone. Yeah, it's very close. Yeah.
And happy Chinese New Year as well, everyone. Thanks a lot for coming. And that's everything.
So, Professor Zhang, do you want to make any final comments? You are the creator of the webinar.
Yes, thank you very much. I just would like to thank Leo and also Suo for this webinar. Okay, and I encourage everyone in the panelists open your camera and thank our speaker today. Okay, yeah, okay, yeah. Bye bye.
Yeah, thank you.
Yeah, thanks Leo for the nice work. Thank you, everyone.
And